the models that you build, people are trying to reverse engineer them on a regular basis to be able to overcome the kind of security that you're developing with your ML models. So this kind of adversarial scenario, this adversarial machine learning challenge, how is that unique relative to the other kinds of machine learning models that you've built historically?
Totally. So Abnormal Security is a company that builds detection systems for identifying cyber attacks that are coming in through email and through accounts that people have on various SaaS platforms, including email. But things like your Slack, your Okta, your Zoom. And so there's really two kinds of attacks that we're concerned about. One is an account has been compromised, and we're trying to identify that this account has been taken over. The attacker has gotten the credentials, and now the person who's operating this account is no longer the account owner, it's the compromised attacker. And the other option is inbound attacks. There's an email message generally, or sometimes other types of messages, where an attacker is transmitting a payload, which could be a phishing link or a message that's eliciting the recipients to update their bank account information, or perhaps malware, or anything else that's the initial vector to begin a cyber attack. And so the machine learning models that we build operate at the level of individual events, which are the messages that are being sent, the sign-in events that we're observing for these accounts, and a number of other kinds of events. And at each of these events, we're trying to identify, is this an attack? Is this malicious, or is this normal behavior? And this is a very adversarial situation because the person on the other end, the attacker, is going out of their way to try to cloak their actions. They're trying to make the messages that they're sending look as similar as possible to safe business messages. They're trying to sign in utilizing infrastructure and technology that allows them to cloak the fact that they are an attacker, hide their identity, and obfuscates anything that they're doing so that it looks like a normal individual. And so our machine learning models that we're utilizing need to take advantage of what are the things that the attacker might not know that we know, for instance, or how do we try to build something that is resilient to different kinds of modifications the attacker might utilize and can really get at the heart of what separates the normal business traffic and communications from what the attacker is attempting to do.
Yeah. So I imagine this involves a broad range of different kinds of models. So I know you mentioned online in some of our research, we dug up that some of these models involve probabilistic models that are like relatively straightforward, I imagine relatively efficient, all the way up to large language models, which presumably are, they're a lot more expensive to run. They aren't necessarily as fast at inference time. So given the kinds of attacks that you're trying to identify, how do you decide what kind of model you're going to be using for a particular type of threat?
So there's really three kinds of models that we utilize, which each of them try to capture something a little bit different and have different trade-offs in terms of what they have access to, the cost that they require in order to utilize them, their speed at which they can be invoked, and their efficacy at the range of different kinds of attacks they can effectively catch. So everything that we build, all of the models we built, are powered by aggregate signals, which are the most important component of our approach towards cybersecurity. So basically, this is a special type of feature that we build over raw data that then powers all the different kinds of our models. And so this is the sort of foundation of our detection strategy. And so these are aggregates over raw email sign-ins and other kinds of raw events at individual entity levels. So for example, we would aggregate for a particular person all of the emails that person has received and be able to say things like, how many times has they received an email that has this header in it, or this kind of phrase in it, or this kind of attachment that's routed through this IP, utilizes this infrastructure, has this HTML tag. Each of these different kinds of little individual signals that could lead to identifying some information about this email, about this sign-in event, we aggregate at the level of each person who's receiving, each piece of infrastructure that's sending, each piece of infrastructure within IPs and domains that messages and sign-ins get routed through. And through this, we build this historical picture, basically a summarization of everything that's happened up until this point that serves as our foundational feature infrastructure. So this is a very sort of structured way of building representations of features. And so it means that there's now a number of different ways that we can utilize these derived signals in models effectively. And so the simplest thing for us to do is heuristics and rules built on top of these signals. This is already a very heavily data-driven approach. Fundamentally, these aggregate signals themselves are basically simple models. They are basically probabilistic models that demonstrate what's the percentage of time given some condition that X is true. That you could construct these heuristics and rules to look very similar to a Bayesian network on top of these individual aggregate signals with different sorts of conditionals that you're applying and different kinds of derived probabilities that you're building on top of it. The next level of sophistication is basic trained models. So this would be things like logistic regressions, XGBoost, and we like deep and cross networks as our neural network architecture of choice for on this kind of multimodal
Deep
data.
and cross?
Deep and cross networks, yes. So it's
I've never heard that before.
It's a network architecture that's very popular in ad tech. We have a number of people at Abnormal have previously worked in ad tech. Basically, it's a type of neural network where you consume both raw signals utilizing a deep layer as well as cross signals, where basically you build derived signals from your individual raw features and then have those derived signals. So you learn the derivation of your cross signals and then feed that into a deep network. And so the cross layer functions in a way where it can take things like, here's a frequency that some attribute is true, and here's a Boolean signal that says yes, true, or not true. And then you can do like a multiplication of these in order to build like a derived signal, for instance. And so these are sorts of cross features that the space of potential cross features that you can build is very, very large. And utilizing this network architecture allows just to tend to the specific cross features that are most valuable. So it allows you to sort of remove a little bit of the work required to build sophisticated cross features without like having a giant parameter space. And so it's nice for cases where you have both deep embeddings and a lot of Boolean and continuous features that you're consuming at the same time, and you're trying to you want to do something a little bit different with like the dense continuous signals within an embedding and the individual Boolean and continuous signals that represent more sparse information. And so the deep and cross network enables you to, it's like an inductive bias that's built onto that kind of architecture. We utilize normal feed forward networks as well at this in this intermediate category of models that we train, but we like the deep and cross because we've seen good performance with it. And there's nice implementations online.
Yeah, that's very cool. So I hadn't heard of this kind of like cross layer specifically in a deep neural network before. In my mind, I imagine the workhorse layer, a dense layer, as being capable of doing some of the things that you're describing. So a dense layer should be able to, in many circumstances, identify whether a cross of two input features are together creating a lot of signal, because that dense layer, that what that means, that denseness is that it recombines any possible inputs from the preceding layer. So it sounds like this kind of cross layer, as opposed to being a general purpose dense layer that happens to be able to do those kinds of multi-term interactions, this cross layer is explicitly designed to do that.
Yeah, so it's similar to how a convolutional neural network is inherently less expressive than a feed forward neural network, but still more performant on image tasks than a raw feed forward network is. It's embedding in the inductive bias that these particular kinds of multiplications between your features to cross them is a useful thing that you want to do for that category of feature. And so we utilize it when we have these signals where there's like one signal that tracks the frequency of an event and then another signal tracks the presence of that event, where these are two features that really only make sense when they're combined together and are very difficult to cross with other kinds of signals. It's their poignancy relies on their combination. And so building those crosses explicitly through the cross network is useful for that kind of application.
Very cool. Well, so I digress a bit into this. So you were saying that there's three kinds of model that you
Yeah.
use. So you were describing the first was heuristic models, rules based ones, and then you were kind of talking about intermediate complexity machine learning models. So things like random forests, logistic regression models, these deep and cross deep neural networks. So yeah, I don't know if I missed any there. If you want to go any deeper on that one, or if you wanted to jump now to model type number three.
Yeah, so model type number three is large language models. And so
Right.
this we utilize both the out of the box OpenAI APIs for certain tasks, as well as building our own fine tuned variants of. We've utilized Falcon and Llama and fine tuned those to a few different tasks. And when you think about these three different categories, they kind of grow in a crescending amount of costs required to run it, increased latency and decreased speed, and uh, different characteristics in terms of their ease of use. The first category and third category are perhaps the easiest to use and modify because large language models you can repurpose with prompt engineering, and rules you can repurpose by tweaking things, whereas the intermediate category of deep neural networks and such really requires retraining in order to incorporate new information. And so all three have pros and cons and can be applied to different types of use cases and challenges within the ecosystem of different kinds of attacks we're trying to catch for different customers.
Nice. That's a really good high level summary of the kinds of models that you work with. And yeah, it's interesting to think about how that third tier, those large language models, that they become so complex now that they're actually, as you say, I hadn't thought of it this way before, but they become as easy to use as a simple heuristic model because you change your prompt and they're so flexible. You don't need to be retraining the entire model. Maybe you could potentially in that third category, you could also be inserting in some PEFT layers, and those are then very fast to fine tune. So you could have this huge architecture, like you mentioned, Falcon. It's a 40 billion parameter model, but you could use parameter efficient fine tuning PEFT to fine tune to some specific task of yours. Maybe just have a few hundred or a few thousand examples of some tasks that you'd like it to be able to specialize in, and you can train that in minutes or hours, even though the architecture is so gigantic, because there might only be a million or so, or 100 million parameters that you're training. Um, yeah, in this parameter efficient fine tuning technique, as opposed to trying to do the whole 40 billion.
It is definitely the case that we've observed, at least, that once you go down the route of fine tuning these models, you lose some of their generalizability and ability to adapt them to different tasks. We've fine
Right.
tuned these models as sort of Uber classifiers that can be applied to classification tasks by taking them and utilizing their size and their really deep understanding of raw fundamental concepts and ability to reason as bases for being able to be applied to representations of our data in a text form that they can understand, that then they're fine-tuned to understand better. And we have a couple of different kinds of message classification tasks that we operate, both the just identify whether or not something is an attack, as well as identifying attacker objectives and triaging messages that are submitted to a phishing mailbox product that we operate as well. And each of these are slightly different kinds of tasks that require slightly different kinds of behavior that involve some amount of human interface that we've seen in the past, and that's where we're trying to incorporate large language models to reduce the human burden on the areas that involve that, because the cost characteristics of these models make them very, very difficult for us to utilize them in an application like scanning every sign in or every email that we process. It's really cost prohibitive to do something like that with models of this size. But something that already involves some human interaction is much more manageable to incorporate these models in.